So part 2, ladies and gentlemen, for the cubic. I think Mr. Pennell calls it a squiggle because it looks like, and I actually use, looks like a weird sideways S. Everyone see that? I know it's not really, Mr. Joe, it's not an S, but it's kind of like it, right? It's reflected, kind of weird. Anyways, that's this one. Just a small disclaimer, the cubic, although we like showing it now, it's actually kind of one of the hardest ones to talk about in terms of transformation. But you're still kind of supposed to recognize this, okay? Just to do an extension really quickly, these are also cubics. And I'll just do them over here to show you what I'm talking about. And some of you will figure out what I'm trying to do. This is the traditional cubic. This one is the traditional cubic. Here's another cubic. Some of you are kind of going, they look the same, Mr. Chen. I agree. They don't all look like this. This is this. And some of you are slowly understanding. How many roots are there? No pressure. How many roots? Okay? One. How many roots here? No pressure, I'm emphasizing that. Thank you. How about this one? And some of you are slowly connecting to the polynomials, the degree, right? It can't be 4. And we just looked at the quadratic. Unfortunately, I erased the quadratic one. A lot of you know the quadratic can have 0 roots, 1 root, or 2 roots, maximum 2 roots. Can't get more than that. And that's why I think some of you are still understanding the whole part of this, right? This is your first introduction, kind of eventually, to what artwork is, or what the transformations of computer games, right? Or how graphics evolve, right? Or even in music. These are what's called transformations, where you start with, like, in music, you start with a basic scale, and you build up the chords, and the triads, and the major and minor, and then chromatic sevenths, and then everything like that. And that's how you get music, right? Transformation. And then you change in the keys into bass or just soprano or anything like that. These are called transformations that eventually we're going to learn. But in grade 11 math, we're going to do, unfortunately, the easier ones. Anyways, that's the cubic. The fourth one, unfortunately, it's the new one for a lot of you. And I'm just going to erase this, but it's going to look messy. Because I just erased my grid. Oh, that's okay. The fourth one is called absolute. And I don't think any of you have ever seen this before. Some of you might know what it means. So I'm just going to give you the English definition. Absolute, I know it looks like parallel lines. Some of you have seen this before. It's not parallel lines. That's the symbol for absolute. And absolute means make positive results in those bars. That's all it really is. I know it seems weird. We're trying to introduce it early enough because in grade 12 you will be learning about absolute more in detail. So in short, you actually don't really need to worry about this. However, notice what I'm trying to explain. We're going to use a table of values. So watch what we're going to do. We're going to input -3 into the absolute values. And I'll just show this really quickly what the answer is. So you're supposed to make whatever is in this positive. So the answer, I know it seems stupid, but the answer is 3. Now the correct definition is actually the distance in terms of its magnitude away from 0. That's what absolute actually really means, but it's more common. It's actually just easier to do it this way. And I do apologize if you want to correct me online. When you get to obviously grade 12. Mr. Jen said this, and then technically there's a better reason. In grade 11 right now, I just want to show you. So a lot of you know what I'm going to do for this answer. 3, 2, 1. How about 0? When you put 0 in, it's still 0. How about when you put 1 in? If you put 1 in, 1 is already positive, so it just stays positive. So this is the answer. All you have to worry about for this one. And what does this graph look like? I'm going to use green chalk. Hopefully that's okay. Watch what we get. And then now let's connect the dots. And some of you are slowly seeing this. Hey, wait a second, Mr. Chen. It kind of looks like a parabola, but not quite. Technically, it looks like the letter V. This is the V graph, but it's actually called absolute. So we'll do a review really quick. And again, as a sketch, a lot of students know what I'm doing, hopefully. The absolute value graph, this parent, it looks something like that. Pretty easy. Couple observations. Again, I didn't do the domain and range for the cubic. I should have. The domain and range for the cubic, x belongs to all real numbers. The range is y belongs to all real numbers, because it keeps on going forever. That's for the cubic. For this one, notice the domain and range is exactly the same for the quadratic. Before we continue, any questions? Last one. The last one's called the reciprocal one, and don't feel bad if you're kind of confused. The last one's the hardest one. So let me just erase this. And it doesn't look scary. 1 over x, it doesn't look scary, but it's weird. And so when some of you might need to refresh or read the textbook after I've done this, that'll be okay. Again, I actually don't like how the handout is, so I'm going to do it a little differently. And if you're using a graph paper that I provided for you, ladies and gentlemen, I'm actually going to change my scale. Although I like 1-to-1 scale for teaching purposes, for this question, watch what I'm going to do. I'm going to use every 2 to be 1 unit. There's a reason, okay? But I decided to change my scale just a little bit. Still proportional, right? I think everybody agrees I've kept it proportional. And there's a reason, okay? There's a reason. So I decided to change my scale. That's why with the graph paper that I provided for you, or the grid, it might make more sense. Now watch what I'm going to do for the table of values. I'm going to actually do a really long one. So I'll start at -4, and then -2, and then -1, and then -5, 0, 0.5, and then 1, and then 2, and then 4. There's a reason. Okay, I'm just trying to show you this. And a lot of you know what I'm going to do for this 5th and final one. And again, I apologize if I'm off screen. It's because the graph is actually more important, because that's what you're going to see. So if you need to do this, please pause the video and record it. And so a lot of you know for this equation, this y equals 1 over x. So I'm actually going to do this one, if that's okay. When you plug in -4 into the function, what do we get? Well, we get 1 over -4, which really is the same thing as -0.25. Everybody agree with that? Did I go too fast? This is clearly not great, but what I'm trying to share with you, notice that this number, it's a big number. For some reason, and this got confused Americans, I kid you not, a quarter is clearly smaller than a third. And yet the 4 is bigger than a 3. For some reason, the Americans, this is like a true story, when they were building the quarter pounder, because it's a quarter, they thought this was actually bigger than this, because the 4 is bigger than 3, but a third is bigger. Right? And so when they just tried to introduce it at not McDonald's, but I think Burger King lost because they were giving these third burgers, these huge burgers, they were comparing it. It's like, no, this is quarter is bigger. And so a lot of students kind of get this confused, that the smaller the denominator is, the larger it's going to get. So this answer is -1/2. And you know what? This is actually a nice critical point. So let's just plot this as I'm doing. Notice I'm doing this slightly different. Everyone okay? I'm doing this one a little bit different. So where's -2? -2 is here. And where's -1/2? Right there. Let's see what I just did? Let's keep one more. You plug in -1 into this equation, 1 over -1. I think everybody agrees this is -1. Hey! This is definitely a nice point. Where's that point? -1 is right there. Everyone see what I'm doing? How about -0.5? Can someone from the class help out Mr. Chen? If you do 1 divided by -0.5, what do you think that is? Don't feel bad if you had to use your calculator. It's okay. Athena? -2! Mr. Chen, these are all nice critical points. So a lot of you know what I'm doing, and some say, wait a second, Mr. Chen, this number is small, is it? But it is. If you really needed to do the math, 1 divided by -0.5 would really mean 1 times -2. That's what we're really doing, right? Because division means to multiply with the reciprocal. And where is negative a half and negative 2 right down there. Let's see if someone's actually really, really smart and paying attention to how I've been teaching all along. And that's okay too if you're forgotten. If we plug in 0 into this equation, does someone read Mr. Chess mind? Use your training that I've taught you. Mackenzie? You can't! This is basically a restriction for this, right? Notice, Mr. Chen, you taught us. You can't input 0. So there is no answer for 0. This point here will be nice and helpful in the future. So this is actually a critical point. I'll put 2 arrows. We'll talk about this in a moment. So notice we only have 3. Right? Before we continue, everyone okay so far? Anyone not knowing what I'm doing? I'm plugging into the thing. Let's see if a different volunteer can give us the last 4. Just like that. And there's a pattern. There's a pattern. Any volunteer? Omar.
2. 1, 2.
And just to share with you, ladies and gentlemen, these 3 are next critical points. So watch what I'm doing. I'm going to use a different color if that's okay. No, I won't use this color. I'm doing this intentionally. I'll use the same color. Because technically, this is all one function. It's all one graph. But I know when I teach this, it looks like, Mr. Chen, you're drawing 2 lines. And it seems like, where is 0.5 and 2? It's right over there. Where's 1 and 1? Right over there. Where's 2 and 0.5? Right over there. So some of you are looking at this, unlike our other examples, it looks like there's 6 critical points. But there is a 7th one that might help you. And you can't really see it. So let me explain. This one is actually the hardest reciprocal function that I'm trying to introduce right now. Okay? And if I were to graph this, you might want to look here first, or pause the video, or look in your textbook, or even using Desmos or GeoGebra to graph this 1 over x graph, the reciprocal function. It's going to look something like this. And let's just critically look at this. It looks like I've drawn 2 lines. Everyone agree? But if I were to draw this from left to right, this is what the motions would be. As soon as I get closer and closer to 0, notice where my hand's going. It's going more and more down, 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 down. Some of you can't see me in the video because it only doesn't go that way. And then if I want to keep on going, I have to lift up my chalk and then keep on going. And I wish I was taller. It would come down as it goes forward towards the right, and then keep on going forever. And notice, a lot of you realize it's going to keep on going. So some are saying, what the hell is going on here? This is your first exposure to not 1, but 2 asymptotes. An asymptote is really how it draws the function closer and closer to. So in this case, there are not 1 but 2 asymptotes. And they're really easy, but they're really hard to teach you. The first one's called a vertical asymptote. And we use VA for short. And the other one, and I should have used the other way around, but that's okay. And the other one, using rail talk, is a horizontal asymptote. A good question is to ask, are they more than that? There are some that are more, but for this graph, these are the only 2. And so let me show you where they are. You might want to look here before you start drawing it out yourself. The horizontal asymptote is this line. And that is y equals 0. Notice, that is why when we had to teach you in grade 9, a horizontal line is always y equals some number. It has no slope. Slope is 0. But it actually goes through 0. How about the vertical asymptote? The vertical asymptote is this one. And it's x equals 0. Notice, the blue and the yellow line, they're not part of the data set. Everyone see that? They're not part. But can anyone tell me something interesting about the yellow and blue lines that I've drawn? Anything interesting? Maybe where they intersect? Anybody? Athena? They intersect at 0, 0 is correct for this function, right? And so if you're paying attention to me, why did I leave it here? although Mackenzie was right, when you input 0 into this, because it's a restriction, it doesn't exist, at the same time, characteristically, 0, 0 is the intersection, if I can spell, intersection, of the vertical asymptote and horizontal asymptote. So in some sense, ladies and gentlemen, this is our 7th critical point. The analogy I like using, hopefully some of you have taken chemistry, when they taught you electrons. Electrons are really tiny, and yet they occupy space. And that's why we get bending in molecules. For example, water molecule is H2O. But notice, atoms try to get as far away as possible. And there's these lone pair electrons that cause the shape of the molecule to bend. Now this is a 2-dimensional representation, but water is actually 3-dimensional. And so the space that you're trying to think of these asymptotes, they're causing the graph or the red lines to approach it, but never touch. There's an internet meme, some of you might have seen in math. There's a picture of literally these examples where they have a Gandalf that says, "You shall not pass!" And that's this vertical asymptote, because it looks like the red line will never cross them. So if you're watching at home, just pause the video. You might need to look up the asymptote. They're just regions of space where it actually approaches. And these are the 5 base functions that we have.
Hi, sir.